Okay, so this final question is pretty tricky, but it's I think this was originally like an AP Physics B question, which was the class before AP Physics 1, but it's kind of a good question where we're thinking about math and then we're also talking about it and explaining it. So I think it's not the best representation of one of the qualitative quantitative translation questions that's going to show up on the AP test, but it's good practice. It's good to think about the numbers and then what do these numbers actually mean. So being able to explain and justify what do these numbers, what do they actually mean. So we're going to give this one a look. Sorry that this looks different than the Google form. This is the PDF that I wish I could give you, but then collecting it gets kind of messy. So we're saying a rope of negligible mass passes over a pulley of negligible mass attached to the ceiling as shown above. One end of the rope is held by student A of mass 70 kilograms, who is at rest on the floor. The opposite end of the rope is held by student B of mass 60 kilograms, who is suspended at rest on the floor. On the dots below that represent the students, draw and label free body diagrams showing the forces of student A and student B. So we can do what we've been doing. We're going to follow this process where we circle our objects and then think about the contact forces. So it looks like student A is being contacted by the rope and then also by the floor. So if we're looking at student A, it looks like ropes are going to pull, they're not going to push. So we're going to have this upwards force of tension on student A. So say we have this force of tension on student A by the rope. I'm going to label this, not really for any reason, just because. And then we also have a normal force that's acting from the floor. So we can say, hey, along with this force of tension, we also have a normal force. And then finally, we know that student A exists on Earth, student A has mass, so student A has the gravitational force acting on them. Okay, if we look at student B is in a little bit of a different situation. They're in the air, so if we're thinking about what's contacting them, really the only thing contacting student B is this rope that is pulling on them. And then they also have their own gravitational force. All right, so those are our force diagrams. Okay, so for B, what they want us to do is calculate the magnitude of the force exerted by the floor on student A. So really what we're looking for here is the normal force. They're just asking it in a weird way. So we want to know the normal force. Student B now climbs up the rope at a constant acceleration of 0.25 meters per second with respect to the floor. So they kind of asked us in a weird order. I changed it on the Google form. So student B is accelerating upwards, which means that there is a net force in this system, and we want to use this information to figure out what is the normal force on student A. So what we're going to do is use our equations over here to write out our Newton's second law for both student A and student B, and then use those to our advantage. So we see for student A, we have a positive upwards normal force plus an upwards tension force minus Fg, and that's going to equal 0. I don't think it says exactly. That doesn't say exactly right now, but then later it's like, hey, what would happen if student A went off the floor? But so student A is just kind of at rest, stationary on the floor. They're holding their own. Then student B, we have a positive force of tension minus their gravitational force is going to equal mb times their acceleration. We know that student B is accelerating. They're climbing the rope, so they're going upwards with an acceleration of 0.25 meters per second squared with respect to the floor. So yeah, we have this information. What we want to do though is we want to figure out Fn. So what I can do is come over here and say Fn and kind of manipulate my equation is equal to FGA, if I add that to both sides, minus FT. I can go one step further with it and say that Fg is just equal to mass times G. So the mass of student A is 70. So if we have M times G, I'm just going to call G 10 again just to make it easy. So then what can I write this? Fn equals 700 minus Ft. So it looks like I want to figure out this Fn. In order to do that, I'm missing Ft. So I need to solve for Ft. But we know that we have one singular rope, and the tension throughout this rope is going to be the same at every point. So we can figure out the tension using this equation, then we can figure out the tension here, and then use it to find Fn. So what I can do is then look at this student B's equation, and I'm just going to copy it and bring it to where I have a little bit more space. There we go. Okay, so I want to solve this for Ft, we said. So Ft equals MBA plus FGB if I bring that over. So then we said, okay, the mass of student B is just going to be 60 kilograms. Right, that's what the picture tells us. Yep. And they have an upwards acceleration of 0.25. So we have 0.25 plus M times G, so 60 times, we're just going to call G 10 instead of 9.8, make it easier. So we can say, okay, our force of tension is equal to 60 times 0.25, so it's going to be 15, I think, plus 600 equals 615, I think, right? Because a quarter of 60 is 15, yeah. Cool, okay. So now we know the tension, and we can plug it in over here. We said Fn is equal to 700 minus the force of tension, so minus 615. So Fn is going to be equal to, what is it, 85? Yeah. So Fn, our normal force, is equal to 85 newtons. Calculate the tension in the rope. We already did it. I'm not sure if there's a way to do that. Yeah, I don't know. There's no way to do it without doing them both. So yeah, so Ft is just equal to 615, unless you sub in and you don't even bother calculating. But yeah, cool. So 2 birds, 1 stone, not bad. As student B is accelerating, is student A pulled upward off the floor? Justify your answer. So in this case, we saw that student A still has contact with the floor. There's still a normal force. So there's still a normal force, which means they're still contacting the floor. So we're going to say no, because the normal force is still greater than 0, which indicates to us we still have contact, still have Fn, still have contact with the floor. It's not a lot of contact, it's a pretty low normal force, but there's still contact in the floor. So then for E, with what minimum acceleration must student B climb up the rope to lift student A upward off the floor? So with this one, what we're looking at is we're saying, okay, well, if they're no longer touching the floor, if we have this situation where oh gosh, I don't know why they're like this, but if student A is no longer touching the floor, it means that we no longer have a normal force because, right, they're not contacting it. We wouldn't have the floor crossing our circle because it wouldn't be there, right? It's not part of the system anymore. It's not supplying a contact force. So we want to know what's the minimum acceleration we could have so that student A is lifted off the ground, or other words, that the normal force is equal to 0. So we can use this same setup as before. I'm just going to copy and paste it. Without the highlighter. So we use the same setup, except for this time, we're going to say the normal force is just equal to 0. So in this case, it's a little bit weird, but we're still going to say that the acceleration is 0. We're looking for like the minimum. So picture a situation where they're accelerating as minimally as possible. So let's picture a situation where they're accelerating in such a low amount. So maybe like the acceleration is equal to 0.000000001 as low as possible, which means that m times a is going to be so close to 0 that we're just going to call it 0. So we're still going to say, hey, this is equal to 0. So now we can still go in here, do our thing, except for this time, we don't have the normal force to solve for. We're solving for the acceleration. So ft minus 60 times g is equal to 60a. So ft is going to equal 60a plus 600. And then we can come over here. So ft is equal to fga, which is equal to 70 times 10. We can set those tensions equal to each other because it's the same rope. Great, so now we can just go in here and say, okay, well, we set the tensions equal to each other. We said FGA is equal to 700, which is equal to the tension. In this case, the tension is also equal to 68 plus 600. So we can subtract 600 to both sides. Say 100 is equal to 60A. So then A would be equal to 100 divided by 60, which is 10/6, which is 5/3, which is a bank. Or maybe not anymore, I think. Is the Fifth Third Bank close? I don't know. 1.666 meters per second squared. So if they're climbing at that rate, then we would get liftoff. If we're just checking our work, this makes sense because this is greater than they were doing before. Before, when they were pulling 0.25 meters per second squared for their acceleration, student A was still on the ground. So if they increased their acceleration, then, so like if they were pulling harder, then student A would be lifted off the ground. So if they were accelerating more, if they had a greater net force, then we would see a greater pull on student A. One thing that kind of tripped me up when I was doing this, and maybe there's some confusion about it. So before, when we had like these pulleys, we were saying like, hey, if we have an object here and an object here, if they're connected, then they have the same acceleration. That's what we said before. So in this case, I said, oh, the acceleration for A is equal to 0, and the acceleration for B is equal to 1.666. So this is just a quick little weird thing. In this case, these objects, they're not accelerating together. So that's for a case where we have this is connected to the rope, this is connected when we have the same A, right? We have situations where like, hey, this is connected to the rope, this is connected to the rope, and they are accelerating as one unit. They're just kind of falling, and because they're connected, they're falling at the same rate. Here we see that student B is climbing up the rope at a differing rate than student A may be changing. So because student B is climbing up the rope, it's not accelerating as one unit, right? Student A is like physically, or student B is like physically changing their position along the rope, it's not accelerating together. Student B, by climbing, is changing the acceleration based on the acceleration of the system. So they're not accelerating together like we have when we had like the Atwood machine in that question number 5. So yeah, that's what I got for today. And yeah, let me know if you have any questions.